Yeah, should I start or like
Sir, I'll introduce you. Just
okay.
Yeah. So I'm sharing my screen first. Yes, everyone. First of all, I would like to acknowledge the presence of eminent speaker of the day, Dr. Shubhamay Pramanik. Welcome, sir. Next, I would like to welcome Head PG Department of Chemistry, Dr. Manju Sahni. She has always motivated us to teach new heights of success. And I would like to thank our worthy Madam Principal for always guiding us and motivating us for doing such new endeavors in her absentia. Kanya Mahavidyalaya has the heritage and autonomous institution conferred with star status by UGC MHRD Government of India, with top national and state rankings by India Today survey of best colleges and Outlook magazine for the consecutive 3 years. It is a pioneering institution for women in northern India. PG Department of Chemistry was established in 1950, and it is a dynamic center for research at the frontiers of chemical science. Our ethos at PG Department of Chemistry is to enlighten the students with scientific temper, practical skills, and confidence for their holistic development. The department's strong record of achievements in chemical research is solidly based on its pioneering advances in chemical research, its success in incorporating these advances into teaching and research programs, and its close relationship to industry. The department offers core courses in chemistry for undergrad and postgrad students and has been recognized by DST under FIST programs. The department is flourished with highly qualified, dedicated, and hardworking faculty toiling to achieve excellent and sustained record of academics and placements. So from time to time, department organizes various activities like World Rose Day, National Science Day, Cleanliness Drive, Food Adulteration Camps, seminars, workshops, educational trips, etc. under various schemes. And in continuation to this, we are organizing KMV International Series Chemistry Chapter, a live interaction with our eminent speaker, Dr. Shubhamay Pramanik, on the topic Supramolecular Chemistry and its intriguing potential applications. So I take this privilege to read the CV of Dr. Shubhamay Pramanik. He is a postdoctoral researcher, Department of Chemistry, University of Kansas, USA. He completed his PhD in 2017 from Guru Nanak Dev University, Amritsar. He has more than 10 years of teaching and research experience. He is experienced in handling all types of sensitive organic reactions, expertise in purifying organic products through silica gel, alumina, columns, proficiency in preparation of nanomaterial, research expertise on synthesis of supramolecular host guest chemistry, and many more. He has assisted 5 MSc honors and 4 junior PhD researchers to accomplish their research project work during his PhD tenure at Guru Nanak Dev University, Amritsar. He has published many research papers in different national and international journals with high impact factor. He is a member of editorial boards of many reputed national and international journals. His H-index is 13 at Scopus and Google Scholar. He has more than 524 citations, and he got Best Paper Award in International Conference Asian Network for Natural and Unnatural Materials 2015 at Punjab University, Chandigarh. So he is also selected for international travel grant from Science and Engineering Research Board, SERB, India, to attend first Asian conference on chemosensors and imaging probes in November 2015 at Stanford Hotel, Seoul, South Korea. He is awarded SERB National Postdoctoral Fellowship in July 2017, and the list is endless for his achievements. So we welcome you, sir, for the talk of the day, live interaction with our students also. So welcome to the department. Over to you, sir.
Yeah, thank you very much, Dr. Narindarji, for in detail descriptions and for highlighting my profile. So it's my really privilege and like I will be delighted to present the work with all of you guys. And thank you all of you for joining this interactions presentation. So I would like to share with you some chemistry. Just a minute. So so today I am going to start some glimpses of supramolecular chemistry and its integrating potential that I have been working here, and also I worked in GNU, but mainly I will focus on the work that I have been working here with some brief introduction about the chemistry. So because I know like a lot of like PG students and BSc students are there. So I will try to explain everything like as simple in layman language so they can understand, and then try to leave their attention and interest. So today's topic entitled is supramolecular chemistry and its integrating potential. So everyone knows about that the a researcher and everyone knows about the research. So we know the researcher and scientist. I believe the researcher and scientist is living in everyone who asks queries and answers, including the teacher and the students. So students have always desired to know everything, and they also always go through the like brainstorming. That means like think about new ideas, and they got the experience from the surrounding, and also like researchers is like a child. You know, the children when they're born, after that they grow and they learn how to talk, how to like daily habits. So like the researcher is also a scientist is also like a kid. So we know everything about the phenotherapy indicator. The phenotherapy indicator is formed like a pink in basic pH, because in acid-base titration we always use this indicator. But the query is like, what happened to this indicator? Why they changes this color? This is the scientific queries we should have. Like, so this is the colorless in basic acidic pH because of this hydroxyl protonated form. But at basic pH, these hydroxyl groups deprotonated, and this anhydride linkages is open. So this is pyridine get open, and this quinone linkages has been observed. So that's why the charge transfer complex formed. This is the reason this indicator shows the color change. And another beautiful example, like we always used to do like everywhere in inorganic chemistry, while detection of various metal ions. So we do like the flame test. And it shows that sodium chloride, the sodium shows the golden yellow color, and the strontium shows the bright orange red color. So these are the colors. The reason behind that, because the excitations of the electrons from the ground to excited state, and they revert back to the ground state. That's why they emit their energy, and this is the charge transfer color has been emitted in the burner. So that's why we observe the color. So these are the things like we should concern about that. Like we should query like why this is happening and how this should be explained. So as everyone knows, like chemistry has a wide varieties of applications, including the chemical engineering. There is a petrol that is also chemical, and also the environment or in daily use we use the filter for purification of water. So what is the filter? Filter also have a chlorine layer which filters filter the water, and even we also use the bleaching powder for purification or like detoxifications of waters. So bleaching powder is also like calcium hypochlorite. So these are the chemical. And the other one, the solid state physics, that also we always know, but because everyone using mobile device which have a like organic light emitting diode or liquid crystal display. And also in forensic science we use, and the followed by biochemistry, because we have a body like human body like that has a double standard DNA. And we also use the medicines to cure ourselves. These are the drug molecules that we have synthesized. And also the pesticides used for farming, that is also kind of chemical. And in atmospheric science, like also there is ozone gas and everything, there are like a chemical process, the rain, acid rain. So there is an endless number of applications of chemistry, but just I would like to highlight some couple of them. So now, yeah, and another thing, the chemistry is like a source of joy. Everyone would love to be happy. So the Nobel laureate Linus Pauling says, like, I feel sorry if the people don't know anything about chemistry. Because when we are become happy, then the serotonin is a chemical that has been secreted in our cerebral hemisphere. So this is the amine of tryptophan, which always like has been secreted in cerebral hemisphere. That's why it's called like the feel-good hormone. And now I would like to highlight some of the pioneer scientists in chemistry and as well as Indian science. So first of all, I would like to let you know, like this is the very old scientist, the Lilabati, who is the first Indian scientist and who was the mathematician. Although like she is not a chemist, but she is the first Indian scientist in 12th century. And the middle one, everyone is aware of this familiar face. This is Dr. Marie Curie, who got the Nobel Prize in 1911 for a discovery in rhodium and plutonium element. And also not only that, she is the only woman stands alone within 4 scientists who got the Nobel Prize, and twice. So she got the Nobel Prize twice, first in 1903 in physics for a discovery in radioactivity, and 1911 for a discovery in radioactive metal ions. And in Indian chemistry, her name is Asima Chatterjee, who is the first doctoral student in chemistry in 1944, and she got her PhD from Calcutta University, and she is the first Indian woman to got a PhD degree in chemistry. And later on, she was awarded by Padma Bhushan, and she was the first female scientist elected for the general president of Indian science. So with these pioneering ladies, women who are like a stands for and who has devoted their huge time for contributing chemistry, so they are really like proud moment for everyone. And with that, like I would like to explain that where my PhD journey starts. I think couple of everyone knows about the Guru Nanak Dev University. So from here, like my journey started, and this is the chemistry department where I used to work. So, but also I have mentioned it's looked a little bit funny, but like I mentioned, the South Cafe and Favors, because in our downtime when like it's like got some time frustrated with the reactions and other like research things. So we just rejuvenate ourselves like while taking some break with this like cafeteria. So these are also, I believe, as a part of our inspirations for chemistry. So first, I would like to start the supramolecular chemistry Nobel Prize. And he's the John Mary Lane. He is the father of supramolecular chemistry. They got he, along with Dr. D.J. Clamp and Pedersen, got the Nobel Prize in supramolecular chemistry in 1987 for his discovery in macrocycles and tryptophan. One thing I would like to stress here. So Pedersen got the Nobel Prize without PhD degree. So still, like everyone love to do the PhD, but I believe like even if anyone like are not interested in PhD, don't think about, don't discourage. So anyone can be a scientist, and even you can see the example by here. So just the interest and implications of your knowledge, that is the main thing you should like keep it up. So here I want to share one of the picture that like with Professor Studert, who is the Nobel laureate in 2016, who got the Nobel Prize for his discovery of protection like a molecular machine. So this is the place, like actually we drove with my wife, Dr. Sandeep Kaur, over there to meet with him and like I'm really delighted to share this picture, and he is so nice, and he was really happy to take pictures with the researcher. So this is the thing, and it was my dream came true on that day, like when I met with him and just like we have a conversation for a couple of minutes, and it was a great time. So now I would like to describe a little bit about the supramolecular chemistry, but still everyone knows mostly about this chemistry. But for general idea, like I would stress on like what is the supramolecular chemistry is different from the molecular chemistry, because the molecular chemistry is emphasizes on their covalent bond that is irreversible. But the supramolecular chemistry is a irreversible based on the weak non-covalent interactions. So Professor John Maryland, that's what I mentioned, like this is associated with non-covalent interaction between the host and the guest. And the guest have different size, it would fit within the cavity of the host through non-covalent interactions. So there are different a lot of forces is involved. Now, if we want to like encapsulate anything, so there should be a force to keep things. There are a number of non-covalent interactions placed, starting from the ionic interactions that will be most strongest, and followed by hydrogen bonding, pi-pi stacking, and van der Waals. Those are followed by weak and hydrophobic interactions is the least weakest one. So I will give you a little bit like overview of those interactions, how they play a role. So there's ion dipole interactions. We know that sodium chloride. Sodium chloride has sodium and chloride. They form like a cube-like structure. Here, there is a tetrabutyl ammonium chloride, which have an ionic interaction, and this is very strong. And followed by that, the ion dipole interaction, where the dipole moment has been generated on the oxygen atom, which are directed towards the central potassium. And we know like the 18'6 is mostly selective for potassium. And there is a dipole-dipole interaction, which is the weaker than the ion dipole. But as we know, the acid, there is a carbonyl group or aldehyde, they also have a dipole moment on the carbonyl carbon. So that's why they undergo nucleophilic addition reactions. So they also like a dipole-dipole interactions. Now the hydrogen bonding interaction. This is one of the most important interactions in supramolecular chemistry. And I would like to stress here, like everyone knows about the ice and water. So what is the difference between them? So ice is very hard and strong, stable, because there are strong and stable and organized strong hydrogen bonding interactions between those water molecules, between the H2O. And the liquid water is just the randomly organized water molecules and their hydrogen bonds. And on the left-hand side, there's a double standard DNA. Also involved, there's a 2 hydrogen bonding interaction between the thymine and adenine, and also 3 hydrogen bonding interactions between guanine and cytosine. So these are the really strong pillar for the development of many natural species and human body. And everywhere is these hydrogen bonding interactions we observed in our nature. And the third one is the pi-pi interactions. We starts knowing about the benzene from the very first day of learning chemistry. So the benzene has a flat pi electron range. So they can also undergo like stacking, that is a pi-pi stacking called the H-type aggregate. And this one is the CH-pi interactions with the hydrogen, and there is a pi electron cloud. And there is a slip stack interaction. This one we can call J-type. And the other one is like a different one, the reverse polarity one. Because when there is a strong electron withdrawing group on the periphery, that will drag the electron towards the periphery. So there is a positive charge generated on the middle. So that is a reverse polarity interactions. And we know the van der Waals interactions, that is a very weak force, but still like there is a, if there is a like very close distance, then they'll observe the van der Waals interactions. So this can be measured by NMR, that is a 2D NMR, that is the NOSI, nuclear overhauser effect. Today we are not discussing, but if anybody wants to, I will be happy to explain how we can measure. And the end, there is a hydrophobic interactions. Hydrophobic interaction, this is the hydrophobic part, and this one is also. So if the same thing matches, then the energy will generate. The enthalpy is increasing because of releasing of water molecule, and also the disruption of solvent entropy is increased. So this is a matching of cyclophane encapsulation of inside the cyclodextrin. So these are the parameters and forces are involved in supramolecular chemistry. So how we can monitor these interactions? By using, these are the basic instrument I will explain gradually during my talk. So NMR, mass, FTIR, and X-ray crystal diffractometer. So other than that, there are a lot of instruments, but mainly I am focusing to the basic instrumentations and how we can use this to characterize these interactions or forces. Now we have to design a host molecule. So the host molecule we have to design which have a complementary with the host binding sites, which should fit with the guest. And there is a chelate effect, macrocyclic and macrobicyclic effect, reorganization is cooperative. But today I am going to highlight the chelate effect, macrocyclic and macrobicyclic. There is a krypton effect. So what is the chelate effect? We learn in the inorganic chemistry from the monodentate ligand, bidentate, and tridentate, or polydentate. With increasing the binding affinity, binding units, the binding affinity will increase. So what is the difference between those? The chelate effect is like a acyclic unit, which have a different binding sites, but the macrocycle is an organized and locked geometry. It's a cyclic. So it would have macrocyclic effect and chelate effect. And the macrobicyclic is just a branch, the addition of macrocyclic effect. So this is called the krypton or more for. So I'm going from chelate to macrobicyclic, the binding affinity would increase. So I could examine there are a lot of straps is required for a binding for packing a box. So these are the chelates. But if we have a proper size bag, a different size bag, and we can fill out with our luggage and whatever we have, so it would like a macrocycle because it is enclosed from surrounding, and we have a different shape. So a different different kinds of luggage, we can pack different bags. So this is the thing for supramolecular chemistry, we need different size macrocycles or a host for encapsulating different size guest. So what are the key parameters we require for hydrogen bonding or supramolecular interactions? So different kinds of monodentate ligand we have mentioned here, and chelating ligands, the urea, and also the protonated chelating ligands, the guanidine. So today I am going to discuss about the anion chemistry. So we have used these ligands and which can donate a hydrogen bonding towards anion. So that is starting from the spherical chloride and the linear azide and pseudo-linear succinate and trigonal planar nitrate and tetrahedral phosphate. So octahedral silicate. These are the binding sites has been shown. So we need increasing binding sites with the increasing size of the anions. So now I am going to discuss a few studies about the encapsulation and host gate complex of phosphate. So we are thinking why we have chosen phosphate, because phosphate is really an important organism in biological process, and we have teeth. Teeth also always has a calcium phosphate. So we need the phosphate, and thus for stronger bone we need phosphate. And also it is a very important, everyone we are knowing in 10th standard or 10+2, how the ATP has been converted to the ADP, and then energy is generated. So ATP, ADP, these are also a phosphate linkages. So if the sugar also have a phosphate and double helix like DNA, everywhere is phosphate. So phosphate is a really important ingredient in our body. So here I would like to show you a couple of synthesized molecules that I have worked in my during my postdoc tenure. So as I mentioned you, from different size macrocycles, I'm going to. So these are the 24-membered macrocycle, 28, and this one is 36, and this is 48-membered macrocycle. We have synthesized these macrocycles, and because of like binding different kind of guest. And these are the cryptan that I mentioned, the macro bicyclic effect. These all molecules I have synthesized during my last 4.5 years. And here is also one of the metal ion complex that is a chelate effect. Gradually I will show you how we have used this for binding unit and supramolecular chemistry. So before going to that, I would like to just give you an introduction about the Nmr spectrometer. So here we have a lot of different instrument of different megahertz. So this is the 400 megahertz, and this is 500. We have 600 also, but this is also 800 megahertz. So why the Bruker company is developing more stronger magnetic field for these NMRs? Those are really expensive. Still, right now, 1200 megahertz is also has been released from Bruker. But why this is required? Because you can see from this example, if we increase the megahertz, the spectrum become much more clear and distinct. So the megahertz is increasing, but the positions of the signal remain constant, but the signal intensity and their separation would be very good. Even the coupling constant should remain same. So this is the NMR in 60 megahertz, and you can see the 600 megahertz and 400, how nice and clean because of their separation. So that's why it is very important to develop this higher megahertz NMR to envisage different kinds of complex chemistry where there is an overlap of different signals. I will show you how gradually where we need to use different kinds of magnetic field. So first of all, I would like to show you here the 36-membered macrocycle, which we have used for binding or encapsulating phosphate. So here is the phosphate, and we know that there is a macrocycle have a amide. So NH, amide has a hydrogen bond donor. So this is the phosphate can interact through the hydrogen bonding interaction with these amides. And these are the black dotted line indicates the hydrogen bonding interactions with those amides. And you can see different kinds of charged phosphate has been encapsulated within this macrocycle. So as we discussed the NMR through and how we can observe or monitor the hydrogen bonding interactions or complexity and the stoichiometry of this complex. So first, this compound shows like a triplet for amide. Why this is amide? Amide shows triplet because of the 2Ni+1, we always know the binding multiplicity. So there is an adjacent 2 methylene proton. So that's why 2 + 1, that is a 3. So this is a triplet. And there is a for A proton, there is 2, 2B and 1. 3 + 1, there is a quartet. And there is a triplet for B because of A. And C would show singlet. So this is the NMR for the free ligand. So on addition of the phosphate, the downfield shifting of those amide signal has been observed. So why the downfield shifting is happening? Because of decreased electron density on those amides. So that is the deshielding effect. So that's why it is downfield shifting. So from this behavior, and this has been observed mostly in case of the amide and very minor in case of the A, B, and C. So this clearly indicates that phosphates are interacting with these amides. That's why the NMR. And this is the trend of amide signal moved with the different equivalents of anions. So this clearly indicates like how we can monitor the interactions and what is the stoichiometry. This is the like 1:3 stoichiometry they are binding. Now next I would show like the mass spectrometer, where we can use the previous case. We have seen the binding is happening with the guest and host, but now we have to define the complex and their overall molecular weight. So for that we need the mass spectroscopy. The LCMS is the liquid chromatography with the liquid sample, and this is the GCMS for the chromatography with the gas phase. So we usually do with the LC for bigger molecules and GCMS for smaller molecules. So we have done the LCMS of that complex. And you have seen here, this is the macrocycle and this is the another macrocycle. So if we can compare it, it's like a bun burger. These two are the bun and the burger is like this phosphate layer. Now this is instead of one phosphate, there are a couple of phosphates because of the different binding sites. And now we have to define the molecular weight of this complex. So we have done like the ESIMS positive ion, like actually this is the LCMS, but we can use the electron spin ionization mass spectroscopy, and which shows there is a mass spec here. And this complex clearly indicates there is a 1, 2, 3, there is a 2 phosphate, 3, 4, 5, and 6. So there is a 6 phosphate within 2 macrocyclic sandwich. So by this, using this mass spectrometer, we would be able to know like how these clusters of different anions or different guests has been incorporated within within the host cavity. So now we have seen about the phosphate chemistry. Now I am moving towards little complex chemistry of those anions. I will try to explain things like in layman language. So if you not able to, I will try my level best to make it simple way. So inositol phosphate. What is inositol hexaphosphate? Everyone knows about the cyclohexane ring. This is the chair form, and we learn like the chair, boat, and different Newman projections. So this is the chair form of the cyclohexane ring. So there are like actually R. It should be OH in all places. If there are 6 hydroxyl group on 6 places, so it would be a inositol. So if instead of OH, it should be a phosphate group on those 6 places, that would be a inositol hexaphosphate. Actually, this is a really important ingredient. I will explain you next slides. So there are 9 possible stereoisomers present in the nature. These are all available in nature. So the most important is the myo, and it is more abundant, like around 70 to 80% present in soil. And the next followed by silo stereoisomer. So what would be the difference between those two? So here all positions are equatorial instead of number 2, but here all positions are equatorial. There is no axial position, and this in case of the myo there is only one axial. So I would describe only 2 stereoisomer in this next topic. So now what we're discussing about the myo-inositol. This is the myo-inositol. If all the phosphate groups are present in all 6 places, this is the phytic acid. This is the generic name, but it is called actually the myo-inositol hexaphosphoric acid. So because of presence of labile hydrogen, it can also can form negatively charged species. So the charge can be vary from 0 to 12. This is a huge phosphate sink that is called the phytate. So now we are considering about the conformation of the phytate, as we have discussed early on. So this is the phytate which have a 1 axial, that is a 2, and all are equatorial. So 1A, 5B. A stands for axial, E stands for equatorial. So actually, Agaronov, one of the scientists, he compared with a turtle, like his head is moving upward. So that's why it's called like Agarnov turtle. And with increasing the pH, as we have mentioned, like it would form a base, like a phosphate, because of the deprotonation of those hydroxyl group, because we are adding base. So it would abstract those hydrogen and form water, and the metal will come, which is phosphate. So now with increasing pH, the conformation does not remain as a 1A 5A. It flips to 5A 1A. Now all become axial except 2. Why this is happening? Because of the metal ion. Metal ion stabilizes those axial phosphates. So I think everyone is thinking like, why this is a weird kind of inositol phosphate? What is the importance of doing those kind of things? So inositol phosphate is a really important organophosphate and one of the most organophosphate available in soil. And we daily use, we eat nuts, breads, right? So nuts and breads also give phosphorus. And this phytate is important for our body to a minimal amount. And it's used in signal transaction, cell growth, and different kinds of activities. But if it has been taken as a lot, so it can act as an anti-nutrient. This is the adverse behavior it has. You can see here, if we can add 1 equivalent of calcium hydroxide in phytate, so it would be insoluble. So if we add taken more, rather than required how much we have, so it would act as an anti-nutrient for our body. So the depletion of phosphorus is also possible for affecting the global food cycle. So that's why we are interested in doing this, exploring the phytate chemistry, because actually one of the things is phytate is also involved in enzymatic activity, but those things has not been explored because of their lack of structure and lack of exploration of chemistry. So now, as we have seen, there is a conformational change with the pH. So this is the NMR of this conformation of 1A 5A. I can just get a little bit of descriptions about those, how it happens, like that doublet. This is DT stands for doublet or triplet, and this is quadret, and these are the a mixture signals. So if somebody is really interested, I can explain a little bit more in depth. Otherwise, I think it would be a little bit more tedious or boring. So actually, we have investigated this multiplate by deconvoluting. This is the 800 megahertz NMR we have used. Now you can see that splitting has been changed nicely. So now we can see how those 3 kinds of signal merged within one signal. So that's why it's really important to higher megahertz NMR. Now, when the conformation has changed to 5A 1E, there is a spectrum has been changed. Now 4 doublet or triplet has been observed instead of 3 signal. So now how this conformation has changed with pH, we were really interested to investigate that. So I have recorded the NMR at different pHs by adding incremental amount of sodium hydroxide. So these are the NMR. You can see this is first the triplet, and H2, H4, 6, and 1, 3, 5. So when we are adding base, that means it is deprotonating the phosphoric acid group. So electron density is increasing on the overall molecule. So that's why it is upfielding, because of shielding effect. Only it's a weird little deviation has been observed in case of the H2, because here is the metal ion is also coming, which is deshielding, whereas the increasing electron density is shielding. There is a competition between the two. So that's why little deviation has been observed. But other than that, mostly it has been upfielded. And around 9 and 10 pH, there is a broad signal I observed because of equilibria between the two conformations. And then after 10 pH, the other conformation has been observed. So I also recorded 31 PNMR because of the phosphorus, but I have not shown here. So these are the NMR titration we have done to investigate their flipping or conformational change. So now I would like to emphasize what is the importance of the X-ray crystal diffractometer. So the crystal diffractometer is really, this is a single crystal X-ray diffractometer, which would be very useful to like investigate all the interactions, all the bindings, everything. So now, when I started the project of this exploring this chemistry, there only two crystal structure was reported, 1971 and 2017. After 50 years, another crystal came up. So it was really like a rare chemistry has been explored, and we started working on 2017. After like initial couple of years struggling, finally we able to got one of the crystals, the potassium salt. That is the first crystal of at basic pH. That is a 1A5E. Other one is 5A1E. So like actually when I was talking with my like supervisor, and then like I was really interested to see their chemistry with macrocycles, because those are the host case chemistry we want to explore. So here I would like to give you one of the example. So as I have shown, this is the 3+3, like 36 member macrocycle we have used, and we already saw these amide groups are involved in interaction with the phosphate. So this is the crystal structure. This is a practical solid state structure. So here you can see this is like a rocking chair like shape. This was is inward, downward, and this is upward. But if we will add the phytate, so what will happen? So the pH was 8.12 due to the addition of the phytate. Because of hydrogens, the pH drops to 6.26. Now, this nitrogen, these are basic. So in presence of acid, these got protonated. So this nitrogen's protons on the nitrogen is just holding those carbonyl group. And you can see here one of the molecule. Now this arm is flipped back to on the top and forming a crown shape. So that's why there is a, for two molecule, like a protonated form, there is an open up, there is a cavity for the gas, like a phytate. This is a really big molecule, and I was able to successfully get the crystal. This is the monoclinic crystal we observed here. Actually, I have given an animation how it is rotating. Just we need to consider just the P2. You can take a look only at the P2 signal, because the P2 is here axial, and other than that, all are equatorial. So that means this is a Mayo stereoisomer. Why I'm emphasizing here the stereoisomer? Because next slide I'm going to like show you the different stereoisomer with the same macrocycle. So we were really happy to see that this macrocycle is bind this Mayo stereoisomer. But actually, while discuss like with the crystallographer Victor, actually we were thinking to investigate and publish an article. So then we observed another different kinds of crystal, like along with these elongated crystals. That one is monoclinic, that one is phytate, and there is a nice symmetrical square-like shaped crystal, rhombohedral actually, observed. And we just take a look at those crystals, and on diffraction, it shows all are equatorial instead of one axial phosphate. So we have seen earlier, there is a one axial, that is Mayo. If there is all are equatorial, that means that is a silo-inositol. So you can see the over top view. These are all like practical structure, the crystal structure, not like a Gaussian or structure. So now from top we can see this is actually acetonitrile sitting on the top on bottom. This is S6 symmetry, and we did like Newman projection. If we can rotate it by 60-degree angle, it would be really symmetrical, very nice star-like molecule. So now we were really concerned, like what is the source of this siloform? Because we have purchased like a Mayo-inositol, that is the isomer we purchased from the sigma reach. So how this other stereoisomer came up? Because like the sigma also, we contacted sigma, and they mentioned they extract this stereoisomer from the rice grain, so natural sources. So there might be a possibility of isomeric impurity. So that's why we recorded an NMR at 800 megahertz of that sample that we purchased from Sigma. There is a very tiny additional signal has been observed, that is a 3% of stereoisomer along with all other myo. So this is actually HSQC, like 2D NMR we observed. We confirmed the position of the sil, and this is a 31P and this is the 1H. So from this NMR we confirmed that there is a stereoisomeric impurity which is present, and this macrocycle was able to separate those two different stereoisomeric forms. And now on top of that, as we have seen, like the phosphate, those are hydrophilic, right? And those macrocycles on top, those are carbon and hydrogen. So those are hydrophobic. So hydrophilic things will love water molecules. So these are the actually real water molecule on the surrounding, which are interacting with the phosphate. And this is actually the macrocycle on top. And this is the silo and this is the myo. For both the structure we have observed there is a water molecule. Actually, I have removed the hydrogens that would show like as a white to make it clear. So these are the all water molecules surrounding these phosphates. And this is really beautiful like you saw. So we were really interested to see their stability, measure the stability in like aqueous solution. So I recorded the diffusion ordered spectroscopy NMR. What is that, the diffusion? Because if we have a different kinds of shape, like a small molecule or a heavy molecule, like a heavy weight and small weight, if we want to push it or move it like the heavy one, so we need, it would be slower, like if we are pushing it at the same rate. So the heavy molecule will move slowly and the smaller will move faster. This same thing is happening in the NMR. So this is the macrocycle which moves faster. When it forms the complex, that will move slower. So here is the result. So the complex would diffuse slowly compared to this host and guest separately. So we have seen here, this is the host, diffuse at 9.8 angstrom to diffusion diameter. From Stokes-Einstein equation we have and this is like 15, the diffusion is here 1.01 and the diffusion is 0.71 for the complex. So it is much slower. So from that we have got the diameter, and which is exactly similar with the crystal structure. So this is the NMR result in the solution phase, and this is the single crystal result from the solid state. So these are really, really close. So that really indicate that these complexes also exist in solution phase, and we can monitor their shape and the size in the solution phase through Dozier. So after anion chemistry, I would like to like the macrocyclic effect. Now I would like to little bit highlight about the chelation. After that I will end. So the chelate effect is the metal complexes. So here we would use the FTIR instrument, and everyone know about that. FTIR is a like instrument that is used to monitor the functional groups, and importantly the carbonyl functional group, which lies between the 1800 to 14 or 1500. So, but before going to that, like I would like to describe, there is a low barrier hydrogen bonding. So initially we have seen the hydrogen bonding distances, which varies from 2.5 to like 3.1 angstrom. But if it is hydrogen bonding is less than 2.5 angstrom, so that means this hydrogen is hopping in between the two electronegative oxygen atoms. So that is called the low barrier hydrogen bonding. So we have observed this one in case of the metal ion complex. So I have synthesized this molecule with complex with palladium. Here's the palladium remains as a +2 charge, and the nitrogen are mononegative. So the charge has been balanced by this nitrogen, but there is an additional negative charge on the fourth coordination side, that is acetate. So who will balance this additional negative charge? These hydrogens. These are the H+ is lying in between these oxygens. And you know, like oxygen are electronegative, so they would repel each other. But because of presence of hydrogen in between them, this is the crystal structure. You can see this is the hydrogen is sitting in between those oxygen, making them flatter. So we also investigate the NMR, and there is a signal at 19.43 ppm. This is very way downfield for this proton, and integration is 2. So we confirm that this is the signal is correspond to the low barrier hydrogen bonding. If it is a normal hydrogen bonding, it should lies on between 10 to 12, but it is a low barrier, and it is 2 electronegative atom is adjacent to the hydrogen. That's why it is way downfield shifted. And the FTIR also, of course, like we are going to do, record the FTIR for this complex because of the carbonyl functionality. This is the ligand without metal complex, and it shows the carbonyl function group at 1668. But with carbonyl, with palladium, it shifts to the lower wave number, like 1600 or 1620. So why? Because the force constant in the FTIR is directly related towards the wave number. Because of binding of the palladium, this double bond character of those carbonyl complex, carbonyl group, is decreased or reduced. So that's why it moves towards the lower wave number. So as we have discussed, like this is the palladium complex, and it should be planar because of hydrogen. But if what happens if we will remove those hydrogen by addition of base? So you can see here on both the structure, because here the oxygen is present, it is flat. But if we will remove those hydrogens, so it would be puckered shape and it is twisted. Normally, the benzene ring should be planar, but because of electronegative repulsion between the oxygen, in absence of this hydrogen, it would be like a twisted one. So these are the all single crystal structure like I developed. So this is under investigation, like under communication, like we are trying to communicate it soon. So with that, I would like to conclude today's topic. So we learned a little bit about the supramolecular chemistry and their different kinds of interactions involving hydrogen bonding, van der Waals, and ionic interactions. So which can be also monitored by using different instrument NMR, ESIMS, and FTIR. And also different size cryptand has been developed for encapsulations of oxoanions, clusters, and inositol phosphate. And we also, of course, like we can do the DOSY NMR to diffuse to measure the solution complex, to measure the size of the solution complex. And also we have seen the Killet effect in the palladium 2 complex with low barrier hydrogen bonding. So for the inspirational message, I would like to say from in continuation of like Antonio Lavoisier and the great teacher Liebig, the study is the past history, you should define the future. So I would suggest, like I also follow that rule, like the agenda of my life, like the read, learn from the experience and implement your chemistry knowledge towards society. So in that way, we would become, everyone can be successful. So with that, like I would conclude, and then I am actually working as a associate editor in the catalytic reactions and chemistry in Frontier Chemistry Journal. So like if anybody is really interested, you're welcome to submit article. And there is a recent issue has been especially for the omens in catalysis and photocatalysis. So another journals like in symmetry, like I'm co-editing for the supramolecular chemistry articles. If you are interested, or if somebody is interested, feel free to pass this information and just submit articles. And with that, I would like to acknowledge my postdoc supervisor, Professor Christine Baumann-James, and their funding agencies, NSF and DOE, and Professor Manoj Kumar from Guru Nanak Dev University, and my CSR grant for my during my PhD tenure. And I really thankful to both of them and also associated members and everyone. So whatever I've learned and where I stand. So and last but not the least, I would like to thank KMB College and Dr. Arinderjit Kaur, and also the HOD ma'am and the principal ma'am for providing me the platform for present my research work. And I would be really happy to answer your queries. And I would be delighted to answer as much as possible I can do. So thank you very much for your attention.
Thank you so much, Dr. Pramanik, for your sharing your knowledge with us and your words of wisdom. So I would like to ask from the participant, if they have any query, they can ask from Dr. Pramanik, if they have any question or anything in their mind. So Haraman Preet is there. Yes, what's your question, Haraman?
Good afternoon, sir.
Yes.
My name is Haraman. Your talk is very useful for us because we are studying spectroscopy these days in our semester 6. And my question is how you get the idea in that your work.
Like you were asking about the basic idea, like actually, I have been working like on supramolecular chemistry and material chemistry in Guru Nanak Dev University. So after that, when I joined here, here research group, actually Bomb Engines research group worked mostly on the macro cycles. So actually, when I joined, she just mentioned me like I have to work on the phytate, that is the Inositol Phosphate chemistry that I have shown a little bit, although I have done a lot. And first 1 year, actually, I little bit struggled to design and synthesize something which could work on those big things. So as I mentioned, to comparison, like the same macro cycle I have used for phosphate and inositol phosphate. So because of the phosphate was as a trial, like actually I want to try mimic the same thing, that is a inositol phosphate, the big one. So I would suggest before going to the big, we should make a model compound or model reaction, whatever you are doing. So from that perspective, I tried to synthesize some big molecule which can fit with those, and I tried the same functional groups to interact with the same way. Like I would suggest, like in lay language, just I read from the literature a lot of things like which might work, and tried. Actually, I got these results after like almost 1 year of work. Like I did not got anything like within first 1 year. So after that, I observed, like I did a lot of things, but there are few glimpses I have shown which are successful, but there are a lot of things was unsuccessful, which I have not shared. So try your level best and read a lot of literature. That is the key to success.
Thank you, sir.
I hope you got your answer, right? So anybody else, any other student, if she wants to ask any question? So thank you so much, Dr. Pramanik. So I'll now invite our head of the department, Dr. Manju Sani, for her vote of thanks. So over to you, ma'am.
Good morning. Am I audible?
Yes, ma'am.
Yes.
Good morning to one and all. At the outset, on the behalf of PG Department of Chemistry, Kanya Mahavidyalaya, I extend my hearty thanks in gratitude to our resource person, Dr. Shubhamay Pramanik, for gracing the occasion. Dear sir, we are really enlightened with your knowledge and presence. Your years of research and your ability to present the subject in such an interesting way produced memorable moments for us. We are truly grateful for the time and effort you took to share your thoughts and experiences with us. We really hope that our paths cross again and collaborate for such interactive sessions. Wholeheartedly, I must thank the principal ma'am for her support and guidance for organizing such an event. My heartfelt thanks to students for active participation. Once again, thank you very much, Dr. Pramanik.
Yeah, thank you very much, Manju ma'am. Like, it's really my pleasure to present like with you and like everyone. I appreciate all of you for joining, and just I would like really happy to share my research work with all of you guys.
Thank you, sir. Thank you very much.
Thank you so much, Dr. Pramanik, for sparing your valuable time. So we hope we will collaborate further in future also. So
Yeah,
thank
sure,
you so much.
sure.
Thank you.
Thank you.